for this last example, we've got a UDL and a line load here. And so I've already drawn a free body diagram to figure out the reactions. And so to figure out the reactions, it's fine to turn the line load into a point load. The magnitude's the area under the line load, and the position is the centroid of that shape, or the center. It's more a centroid. It's not really a center of gravity. It's the centroid of that shape. And so I've found that in its position, and then I've used all that to figure out the reactions. It's a fixed support this time, so you've got a moment and a vertical force. We don't have a horizontal force because there are no horizontal forces. And in all the problems you'll do, there won't be any axial forces. There won't be any horizontal components to the forces for these free body and bending moment diagram questions. There might be for questions where you're just finding the internal forces at a point, but not for these ones where you're drawing free body diagrams. You've got enough to do without also drawing the axial force diagram. So, calculated that. I don't think there's any particular issues in there. To draw in the direction for this, I just figured out which way the moment would need to go to hold this up at the reactions. And so remember, this is an external force, not a fake one, so we don't use those internal forces signs to figure out the directions for these. Usually what I do is just figure out what I think they are, and if it comes out negative, I need to change the direction. And usually when I'm doing shear force diagrams and bending moment diagrams, I just redraw it and then redo the calcs so that it is right. It does come out positive because you need it to be the right way when you get to doing your shear force diagram. Otherwise, you can end up accidentally going the wrong way. Now, so what's next? I think we just go straight on with drawing the shear force diagram. Too easy. So, what I have done though is I don't carry this point load through to this when I'm doing the shear force diagram. Writing down that equivalent load or changing this to equivalent load is only valid when you're looking at the external forces, the reactions. It's not valid when you're looking at the internal forces in the beam. The internal forces for this loading will be different from these ones. For example, this has no loading on the end, so there'll be zero shear and zero moment at the end, whereas this one does have loading right up to the end, so it's going to have a shear and a moment right up to the end. So having said that, let's go on. So we've got a point moment, or we've got a pure moment, or we've got a couple, but shear force diagrams don't care about those because they don't have the forces cancel out for couples, and so it doesn't have any y component of force. And so then the first thing we are going to do, I'm just having a think about this. I don't know why I went up to 20. Let me just redo that. So we're going to have 5, 10, 15, 20. I've just done the same thing again. Very clever. So we've got 10. So that's like 5, 2.5 in between. Now, so what have we got here? So we've got a line load. So we know the shear force diagram is going to be a line, and it'll probably be at an angle. And to figure out how much the shear force changes, we just look at the area under the line load. So if we move 1 meter, it's 2 kilonewton meters. So we do 2 kilonewton meters times 1, so it's going to go down 2 kilonewtons per meter. Sorry, should be 2 kilonewtons per meter for line load. So 2 kilonewtons per meter, times it by a meter, you're going to get 2 kilonewtons for every meter you go along. But it's just a line load. It's going to be straight, so I'm just going to do it straight to the end. 2 times 5 is 10, so we're going to go up 10 to start with because of that force, and then it's going to come down gradually for that UDL, and the total change is going to be the total area under that line load, and so it's going to be like that. And that's the shear force diagram, and you can see that's different from, where's the one we did before? We have one that was actually a point load. Let me just find it, this one here. And so completely different. And so it stays constant shear and then drops straight off when you get to the load, and then the load goes down, stops. The bending moment is 0 by the time you get to the load, whereas for this shear force diagram, it's gradually decreasing the shear force because you're slowly adding on more load that counteracts this reaction. So the shear is highest at the support. Bending moment diagram now. Okay, I know it's all going to be negative, How do I know it's all going to be negative? Because I can imagine what it looks like. So it's going to be like this. It's going to look like that. And so we are going to have hogging. So it's curving down the way like so. And so we've got a hogging moment. So it must be negative, and negative is in the upwards direction on a moment diagram. And so I can figure that out. Now, for moments, if we come across a couple or a point moment or a pure moment, you kind of do the opposite of whatever it is. So this is a positive moment, it's a clockwise moment. So that means it makes the moment diagram jump in the negative direction. Again, the moments, for moments, your signs are all over the place. It takes a lot of remembering. But again, I'm thinking back to what it'll look like. I know it must be a hogging moment. So therefore I know it must be negative. And so you're kind of cross-checking a few different ways to make sure you're on the right track. Then what do we know? Well, we know that for 1 meter long, the amount the moment diagram is going to change is going to be equal to the area under that shear force diagram. Shear force positive, it's going to head in the positive direction for moment. And so therefore, let's just have a think about this. So it was 2 kilonewtons per meter, so it's going down, just draw it on. So it starts off at 10, probably should just, usually do just stick on what the maximums are. Yeah, I left that behind. There we go. So this here is 10 kilonewtons. So this here, if it drops 2 kilonewtons per meter, 2 kilonewtons every meter, this must be 8 kilonewtons. So the area under this part, you can do it with a rectangle and a triangle if you want, but otherwise you can just take the average of these, 9 kilonewtons times 1, so it's going to go down by 9, 25. Now, go down, which is going in the positive direction because positive shear. So it's heading positive by 9. 25 minus 9 is 14. So it's going to come to here somewhere, 14. And it's going to get less steep as it goes along. You can see why, because each time the area is getting less, so the change in the moment is going to get less each time. And so it's going to be something like this, if you know what I mean. So let's just get another point now. So if we go down 2 kilonewtons per meter, whoops a daisy, then this here is going to be 6 kilonewtons. And so the area for the next meter, the change between here and here, is going to be, average of those, 7 times 1 meter, 7 kilonewtons times 1 meter. So that's 7. 15, take away 7, is going to be 8. It's going to be about here somewhere. Okay, we can just keep doing that the whole way along. Nope, 4 kilonewtons. The whole thing's going to be 5 kilonewtons times 1, so it's going to come down another 5, so it's going to come down to 3 now. This one is going to be 2 kilonewtons, 3 times 1, so it's going to come down another 3 to 1 kilonewton, somewhere here. And then you've got 2 and 0, so that's going to be 1, and that's going to bring us back to 0, which is what we expect for the end of the beam. Okay, we should have 0 at the end of that beam. There's no forces after that, no moments after that, so it has to come back to 0 at that point. You could figure that out by just taking a section on the other side. So you could take, so if your beam was like so, just take a section right at the end and just do all your section stuff for that. And you could just double check that why that's the case. So therefore, we just draw a line through all those points. We draw a curve through all those points because we can see it's curved. And we're done. And a shade under. Nothing really more to say about that one, really. Good. So we'll just do one more, I think I've said this a few times now, one more example with a slightly more complicated example. We'll go back to one of the examples we did before, and we'll do the moment diagram for one that's got a few different loads in it.